Hi and welcome. This is our session number 9. Last time in session number 8, I was talking about the chain rule, some applications of the chain rule. I gave two examples that show that the chain rule is really an important thing. It makes many things easier and makes some things possible that were otherwise not very clear. Okay. Today I'm gonna be moving into talking about product spaces a bit. Before that, I'm going to be talking about the differentiability of the inversion map, which we already saw that it's continuous previously. So we're talking about this map phi, which goes from isom EF into L of EF, okay, which takes each u to its inverse. So phi of u equals u inverse. This thing we already showed that it's continuous. Okay, of course the assumptions have to be correct. We need E and F to be Banach spaces, okay, and of course E to be isomorphic to F, because otherwise this isom is empty. Okay, we want it to be non-empty. So I will state our theorem very clearly, and we'll proceed to proving it. Now, as for the intuition, so phi is the inversion map, sends every u to its inverse. We expect this thing to be continuous away from places which might make some trouble. For instance, let's look at the one variable real case. We talk about the function x maps to 1 over x. This function which is going from r minus 0 into r. Okay, this function is differentiable wherever there is no trouble, of course. Yeah, right. I mean, on its domain, which is r minus 0. Its derivative is given by minus 1 over x squared, and we expect something like this to happen inside. Or for the map phi, which we just talking about now, we expect that its derivative looks something like this. Okay, but of course, because we don't have squaring when you have maps, of course, unless we are in an algebra. Okay, in this case in a Banach algebra. But generally speaking, we cannot just square a map unless there's a well-defined notion of multiplication. We're talking instead of composition of maps. Okay, that's the thing we're going to be talking about. And to see that phi is differentiable and to find its derivative is not really a difficult task, as you will see now. So let's start with this theorem. Okay, remember we are now we're in chapter 2, okay, chapter 2 of Cartan, and in particular we're in section 4, okay, section 4 of chapter 2. So we're in 2.4 of Cartan, okay. Now this theorem, okay, it says that let E and F be Banach spaces, okay, such that E is isomorphic to F, okay. And consider phi from isom EF into L of EF, okay, given by phi of u equal to u inverse. So for each u in isom EF, which if you recall, so isom EF was the space, was the set, okay, it's an open set. The open subset of L of EF consisting of all maps U in L of EF such that U is an isomorphism, okay, in the sense of known vector spaces. So linear algebraic, so in the sense of linear algebra, isomorphism, so bijective linear map, okay, which is bicontinuous, which means that it's continuous, okay, bicontinuous means continuous and inverse is continuous, okay, so that's what a bicontinuous map is. So we're talking about the subset, so isom EF again, the subset of L of EF, the space of all. So we're recalling a few things now just to refresh. Okay, so L of EF is the space, the vector space, okay, of all the norm vector space actually, okay, norm vector space, so it with the norm of all linear bounded, or if you want continuous, okay, maps from E into F, okay, and the isom EF is the open, which we proved as an open subset of L of EF, which consists of all the maps U, okay, linear continuous from E to F, which are isomorphisms, which are isomorphism in the sense of linear algebra. So they are linear maps which are bijective, and they are bicontinuous. So they are continuous, they're continuous inverse. Okay, and this map phi we discussed earlier in one of the sessions, and we noted out that phi is a continuous map. We proved this thing actually. Phi is continuous. So yeah, now, okay, this theorem, back to this theorem. So consider this phi, okay, then phi is differentiable on isom EF, on all of isom EF, okay, and d phi at a point U applied to H equals minus U inverse around H around U inverse. Or if you want, you can skip the composition, so it's minus U inverse H U inverse, with understanding that multiplication here is composition of maps. Okay, and moreover, d phi is continuous on isom EF, and this makes, so in other words, okay, phi is of class C1 on isom EF. Okay, so a class C1 just means differentiable with continuous derivative. Okay, in fact, later, later we'll show that phi is of class C infinity on isom EF when we define higher order derivatives. Okay. Now we'll leave this for later, of course, when we talk about higher order derivatives. For now, okay. So what's the proof of this claim? So first of all, let's try to construct d phi from scratch. Okay. Of course, in the statement of the theorem here, we are mentioning what's the d phi. Okay. And if it makes you comfortable, you can just prove the theorem using this expression. Okay. Just subtract this expression and try to prove that you have what you want. So first way, try to prove, okay, that phi of u plus h minus phi of u minus d phi of u at h is little o of h, using the expected expression for d phi of u applied to h, given by the statement of the theorem. But this is cheating because you are relying on the person who stated the theorem, who is telling you that this is the derivative, right? And the second way, of course, is to directly prove it. Directly do it, i.e. construct d phi at u h from scratch. Okay, let's try to do that. So we'll look at the difference. So of course, when we want to find the derivative of a map, we're gonna need to look at the difference phi. So let's say let u belong to isom EF. Okay, and let's perturb u by an h. So let's look at phi of u plus h minus phi of u. Our target is to make this equal to, find something is equal to, okay, something in h plus little o of h, and this something here will be the linear something here will be the d phi of u at h. Okay, so let's do that. So what's phi of u plus h minus phi of u? That's just simply u plus h inverse minus u inverse by the definition of phi. Okay, let's factor out by u plus h inverse. So that's u plus h inverse, factoring out from the left. Okay, what we are left with inside is 1 minus u plus h times u inverse, so to speak, times. Okay, because there's no multiplication happening here. Again, there's just composition of maps that's going on here. Okay, so if I want to write things super clearly, okay, so super carefully, this is u plus h inverse composed with identity map, where of course the one here is the one which is compatible with these guys. So u inverse is going from f to e, and u plus h is from e to f. So this is 1 of f, or if you want the identity of f, minus, okay, u plus h composed with u inverse. Okay, that's the completely careful way of writing it, but we will not be this careful because at the end of the day, for our purposes, composition acting just like multiplication. But we have to, of course, be careful that this multiplication is not commutative and so on. Okay, so it matters where you multiply, from the left or from the right, because it matters where you compose, if you compose from the left or from the right. Okay, so again, to this expression, okay. Now here we can expand, of course, this thing we can expand it, right? But, so let's look at the expansions. U plus h inverse times 1 minus 1 plus hu inverse, right? And this thing is just so let's write this u plus h inverse composed with, or times, okay, minus hu inverse, okay? And this is just minus, to take the minus outside, because at the end of the day, composition, which is what's happening here, okay, is a bilinear map, so you can take the minus outside. This is minus u plus h inverse composed with h, okay, composed with u inverse. That's what we got. Okay, now this thing is the difference. So again, this thing here, let me write it in red. This is delta, if you want, delta phi at u, delta h. Okay, this is usually a symbol used for like something like phi of u plus h minus phi of u. Okay, this is the thing that we did, and we got this thing. Okay, now I want this to look like a linear map in h, depending on u, of course, plus some little o of h. What this means is that I would want this thing here, okay, to be something plus something else, okay, or let me say it this way, okay. Let me take, okay, so phi of u plus h minus phi of u. Okay, this is minus u plus h inverse h u inverse. Let me say this. When I take h to 0, of course, this thing is gonna go to 0. Okay. And this expresses nothing but the continuity of phi at h, because I'm doing difference at u. Difference phi of u plus h minus phi of u. Okay, so the fact that this thing goes to 0 is the expression that phi is continuous at u, which is something we already know. And you can see it directly from here. Okay, now we know that these are have some composition here, and this composition is bilinear. In this case, yeah, it's bilinear and continuous, and there's no issue at all. Okay, so it's composition. Okay, and but this is not something that we care about. Okay, but furthermore, if you divide the right hand side, which is this thing, if you divide it by h, so to speak, okay, so if you're looking at the norm of u plus h inverse h u inverse divided by norm of h, this thing, well, this is not exactly going to go to 0, right? Because this thing, okay, you can say that this is less than or equal to the norm of u plus h inverse times norm h times norm u inverse. I'm not saying it's not going to 0. It's not necessarily going to 0. You cannot conclude this from here. Okay. Now, if we cancel out these guys, we are left with norm u plus h inverse times norm of u inverse. And this thing just simply goes to norm of u inverse squared. Okay, because this thing here will tend to norm of u inverse. Okay, because again, inversion is continuous. But this thing is not useful, of course, because I want to divide by norm h and get something that's going to 0. So to do this, one of the ways to think about it is you think, okay, I have now minus u plus h inverse h u, or was it u inverse? Okay, h u inverse. Okay, and I'm looking for something, okay, to subtract from this. So this minus, let me write it, do it in another color. Okay, minus something, okay, when I divide it by the norm of h should go to 0. Okay, so let me think about this way. So I have minus h divided by u plus h times u. I pretend that I have this thing, okay, just to better see things, okay. But of course, this does not make sense. This does not make rigorous sense. So no rigorous sense to this. Why? Because you simply cannot divide by functions unless you have a well-defined notion of division of functions. Okay, so this generally does not make sense. But okay, if I want to look at this and say, okay, I want to subtract from this something. Okay, I want to subtract from it some a, such that when I divide this entire thing by h, I'm gonna go to 0. Okay, so pretending everything we have here is scalars. Okay, so let me just divide by h right away. And of course, since I'm looking at a difference, okay, or if you want, since I have minus signs here, I have a minus sign here and minus sign here. If this thing is gonna go to 0, okay, then minus times this thing is gonna go to 0. So let's just ignore the minus sign. Right? H over u plus h u, okay, plus a divided by h. This thing should go to 0. Okay, so I have 1 over u plus h times u plus a over h. Okay, this thing should go to, so don't need parentheses anymore, this thing should go to 0. Okay, and then if you do a common denominator, you're looking at h plus a times u plus, so to speak, times, okay, times u, okay, divided by h u plus h u. This thing should go to 0. Now notice something. If a itself, okay, does not contain an h in a separate manner. So what I mean by this, if a does not look like h times something, okay, it's tough to guarantee that this fraction here will go to 0, right? Because if you cannot cancel out the h somehow from downstairs and upstairs, okay, you might have something that looks like a number over 0, and this thing will blow up. Okay, so I don't want this thing. So I will assume that a looks something like h times b. Okay, and that's what I substituted. I have h plus hb times u plus h times u plus h times h times sorry u. Okay, divided by h. This thing should go to 0. Now cancel out the h's. Okay, and you get yourself 1 plus b times u plus h times u. This thing should go to 0. Okay, now for this thing to go to 0, this b times whatever is here should behave in an opposing manner to 1. Because I have a 1 here, so I have a 1 here. The only way 1 plus something will go to 0 if what I'm adding to 1 is tending to minus 1. So this thing should go to minus 1, right? Because then you had minus 1 is equal to 0. Otherwise, you cannot get a 0 limit, or if you want, you can just rearrange. Okay, take this thing to the other side of the limit, so to speak. So you get that b times u plus h times u. This thing should tend to minus 1. Okay, now minus 1 in our context is just minus times the identity. Okay, and here we are starting to go back to the composition of maps work frame, which we are in here. Okay, so I know that b should look something like minus. Okay, it should involve u plus h inverse, and it should involve u inverse somehow. Okay, so minus u inverse. There's no particular order, but I'm saying there has to be something like this inside b. B has to look something like this. Okay, and so a, which I started with and said, okay, there's an h. A, which is h times b, should look something like h. So it should have minus sign, and h, a u plus h inverse, okay, and a u inverse. Right, and this is really a very close form to what we have here actually. Okay, we're gonna see that the appropriate thing to do here is, of course, to subtract by something that looks like this. Okay, and when you see h going to 0, you see that it does not matter anymore to have u plus h per se here, because at the end of the day, u plus h, so as h goes to 0, u plus h inverse itself will go to u inverse, because phi is continuous, i.e. u maps to u inverse, or if you want just not to use u, v maps to v inverse is continuous, and therefore you can insert the limit inside, and therefore this will go to u inverse. So actually I'm looking at a being minus h u inverse of this sort. Okay, sort of. Again, this is just intuition. We're just talking intuition here. So nothing is rigorous here. Okay, I'm talking this sort of thing. Okay, so that's what I expect a to be. Okay, a is the thing which I'm subtracting, which is supposed to be the derivative. Supposed to be d phi at u applied to h. Now, if I look at the order of things here, Okay, so I have first H from this expression here. First H composed with U inverse, composed with U inverse. Now, does this make sense? It does not make sense. U is a map going from E to F. Okay, so U belongs to isom EF, which is a subset of L of EF. So at the end of the day, U is a map going from E to F. U inverse is a map going from F to E. Okay, if I compose U inverse with U inverse, it does not make sense. Okay, so U inverse is a map from F to E, and U inverse again is a map from F to E. I cannot compose these two maps unless F and E are identical spaces. Okay, otherwise composition just does not happen here. Okay, so that's why the order of things here is just not adding up. Okay, not adding up appropriately. So let me try to rearrange this thing into something which will give me an appropriate something which is well defined. Okay, so let's look. So U inverse going from F to E, H, okay, is going from E to F. H represents a perturbation of U. So again, U is living inside isom EF, okay, and I'm looking at phi of U plus H. When I'm doing this, I'm looking at an H in a ball around U, which is small enough to guarantee that we are still inside the isom EF, okay. So at the end of the day, even if we are not staying inside the isom, H is a map from E to F, okay. So both U inverse composed with H and H composed with U inverse, both of these make sense, okay. U inverse composed with H is just going to be a map, okay, this thing here, just going to be a map going from E to E, okay, and this thing here will just, so this thing here, just be a map going from F into F, okay. So it makes sense to do these two operations. However, any other permutation of this expression, which is consisting of U inverse H and U inverse, any other permutation of these guys will not produce a meaningful expression, because any other permutation, any other kind of form, okay, will need to have U inverse and U inverse alongside each other, and these cannot be composed. So that's why this should be avoided, and the only solution is then to have something like this. Okay, so that's why I expect A to be minus U inverse H U inverse, or if you want to keep compositions, minus U inverse around H around U inverse. And as we find out, this is exactly the derivative we are looking after. If we compare this with the statement of the theorem was saying that this is the inverse, the derivative of the inverse. Okay, so that's why what I do now, since I expect this thing, what I do, so next step, okay, the rigorous step, okay, instead of looking just at phi of U plus H minus phi of U, I'm gonna look at phi of U plus H minus phi of U minus U inverse around H around U inverse, okay. And this thing, okay, is just, so what's phi of U plus H minus phi of U? What we got was, so bear with me, this thing here, okay, this is what we got, U plus H inverse, H U inverse, okay, so let's go down, so we got U plus, I guess still the same color, okay, so yeah, so U plus H inverse with a minus sign, of course, H U inverse, okay, plus, so this plus U inverse H U inverse, okay, and this is what, so of course here you can see already these maps are factoring, okay, factoring the situation. This is just U inverse minus U plus H inverse, okay, composed with H, composed with U inverse, if I factor by H U inverse to the right. Okay, now we are very close to getting what we want. This thing here will go to 0 because phi is continuous, okay, and now if I look at the norm of this thing, okay, so remember that this here, what we got here is this thing, okay, which I desire to show that it's equal to some little o of H. Okay, so let's look at this thing here. Okay, this thing in norm, U inverse minus U plus H inverse, okay, composed with H, composed, so let me make the H clearer, composed with H, composed with U inverse, divided by the norm of H, okay, this thing is less than or equal to, of course, the norm of U inverse minus U plus H inverse times the norm of H times the norm of U inverse divided by, or if I don't think this thing will work this way. You can say that this is less than equal to this, okay, times yeah, I mean this will work, okay, and explain why this will work. Okay, norm of h times norm of u inverse divided by the norm of h. Okay, so now we just cross out the norm h and the this thing. So here for this inequality I'm going to explain, okay, in a bit. Explained in a bit, okay. And well, what I'm left with is just norm of u inverse minus u plus h inverse times the norm of u inverse. Now, since this thing here, so this expression here, goes to 0 because phi is continuous, right? It's just what it means for phi to be continuous. So I get that this entire thing will go to 0, okay? And therefore, since when we divide by norm h, we get a limit of 0, we conclude that what we got here, okay, is little o of h, right? So conclusion, so u inverse minus u plus h inverse composed with h composed with u inverse, this is really little o of h, okay? And then since this thing was this difference, okay, I conclude that phi of u plus h minus phi of u minus u inverse round h round u inverse is little o of h. And therefore, this warrants the conclusion that d phi, so therefore phi is differentiable at u, and d phi at u applied to h is given by minus u inverse h u inverse. Okay, this is the first step of the theorem. Okay, since of course since u was arbitrary, this means that phi is differentiable on all of isom ef. Okay, there were no special conditions on u. So phi is differentiable on isom ef, and its derivative is given by this formula. Okay, now regarding this step here, okay, so why is this step warranted? So what I'm actually saying is that I have three maps composed with each other, so g, f, h composed with each other. I'm saying this is less than or equal to the norm of g times the norm of f times the norm of h. Okay, this is coming from the continuity of the trilinear map. So I'm looking at the trilinear map, okay, which is taking g, f, h to g composed with f composed with h. Okay, and we actually showed that this the analogous thing to this, which is gf maps to g round f, we showed that this is bilinear continuous so long as we are working on linear maps, spaces of linear maps which are continuous, so linear continuous maps. Okay, so in other words, so let me write this. We already showed that if I have some E, F, and G non-vector spaces and some bilinear map B going from L off, so just to get things appropriately, I'm gonna do GF maps to G round F. So I'm talking about a map which is going from F to G, map which is going from E to F and landing in EG. Okay, so this bilinear map, okay, takes a map which is F going from E to F, okay, and the G which is going from F to G. It does G round F and it lands U from E to G. Okay, and this bilinear map, this you can prove to be bilinear. We have already did this. Okay, this bilinear is continuous as well. Okay, prove that it's continuous, and the same thing can be done, okay, to prove that a trilinear map of this sort is also continuous. Okay, that's what warrants the conclusion that we were just doing here. Okay, the conclusion that the norms can be separated in this manner. It's composition, and this lands into a becomes a product of norms. Okay, and yeah, so okay, so that's as for the justification of that step. Okay, so an exercise. Let's just do an exercise. Let's just write it as an exercise. If you need anything about it, you can just leave a comment somewhere. So this exercise, let's say we have this trilinear map T, Okay, going from, so just to get things appropriately, I'm taking G, F, H, giving it G round F round H. So I want to take a G which is going from, so let's make this handwriting smaller. T going from L of G, which is going to be the final map. So I'm going to be needing three, I'm going to be needing E, F, G, and big H, known vector spaces. Okay, I'm going from GH cross L of FG cross L of EF, and I'm landing in L of EH. Okay, so I'm taking a map G, let's start with H. H is going from E to F, F is going from F to G, and G is going from G to H. And I'm composing these maps this manner, okay? I'm getting a map G round F round H, which is going from E into H, okay? And it's gonna be a linear map itself as well. It's G round F round H, linear and continuous, okay? And yeah, so prove this thing to be a trilinear continuous map. So prove T is trilinear and continuous. I'm giving this as an exercise because I'm not sure at this point if I gave this before or not, if I mentioned this before or not. I probably not mentioned this thing, but it's very analogous to the bilinear case, which we talked about, okay, and we actually proved. So this is just an easy generalization. Okay, now as for what remains to prove that d phi is continuous on isom EF, okay, let's look at the map d phi. So d phi is going from isom EF, okay, into L of EF, okay, and it is taking a U and producing d phi of U, so d phi at U, which is a map going from E into F to each H. It's giving d phi of U at H, okay. Now we don't care about this many details, we just want to know how to deal with d phi of a perturbation, okay, looking at d phi of U plus H minus d phi of U, okay. Now let's look at this thing, okay. D phi of V generally is what? This thing is minus V inverse composed with, say dot, composed with V inverse, right? Because this thing here represents a placeholder for a variable. And in fact, d phi of V as such is incomplete. It needs one more variable in order to become a fully fledged vector, let's say, inside a vector space, inside one of our known vector spaces. So we say d phi of V at H is minus V inverse around H around V inverse. Okay, now if I try to look at this map here, which I indicated, okay, and I try to define, so let me say psi, okay, this map psi, it's gonna take two vectors V and W, it's gonna produce minus V composed with dot, composed with W. This is a placeholder for a variable, okay, this map, and then it's easy to write, so you can say d phi at U, okay, this is just minus, or let's say it directly, this is just psi of U inverse, right? And then to prove that d phi is continuous, okay, amounts to showing that psi, okay, of say the map which is given by U maps to psi of U inverse, okay, is continuous. And this is a bit easier to do, okay. Yeah, we are ignoring, so here I started with this thing, we're gonna look at this difference, okay, but we're not gonna do the difference actually, we're just saying, okay, we wanna do this difference, but then it's not doable because of the type of this map that we have in our hands here, which needs one more variable, okay, other than the variable it already has, okay, in order to make sense as a vector inside one of our non-vector spaces. So in here, let's look at the map, this thing. U maps to this thing. Okay, U inverse is again what? It's just phi of U, right? Phi is the map which takes you to U inverse, okay? And that's why the map psi actually, or the map U maps to psi of U inverse is just the map, okay, psi around phi comma phi. And when I do this thing, phi comma phi, it means just the map which takes, generally if I say say the map fg, what I'm meaning is the map which takes x and gives f of x, g of x, okay? So yeah, so I'm talking about this map psi around phi comma phi, okay? And I know that, so let's look at psi again. So psi takes v and w, okay, and gives you psi of vw equal to minus v around dot around w. Okay, let's look at this map psi and let's try to find out if it's a continuous map. Okay, so first of all, psi is bilinear, right? Because these variables are free to so if you fix one of them, okay, you're gonna get linearity in the other, right? And you can see it most explicitly by saying, okay, let h be given, okay, and consider psi of v w applied to h. This is going to be minus v h w, okay? Fix v, okay, and let's see if it's linear in w. So psi of v, say alpha w1 plus beta w2, okay, applied to h. This thing is just minus v h alpha w1 plus beta w2. Okay, then you expand. This expansion is allowed because this thing here is a linear map. This thing is linear. Since it's linear, it can separate, okay, the arguments inside it. It's just the minus vh alpha w1 plus minus vh beta w2. Okay, and this thing is just, if you take this alpha, is just a scalar, right? Take it outside. So because composition is a multilinear map. So you get minus alpha VHW1 minus beta VHW2. Okay, and well, this is nothing but psi of, well, let's write it like this. So let's say this is alpha minus VHW1 plus beta minus VHW2, and this thing is just alpha psi of V W1 applied to H plus beta psi of VW2 applied to H. Okay, and this thing, okay, implies that psi of V alpha W1 plus beta W2, okay, is just alpha psi of VW1 plus beta psi of VW2. And this, therefore, psi is bilinear because you can replicate the argument for the v variable, for v being variable and w being fixed. Okay, so psi is bilinear, in fact. Okay, let's see if psi is continuous. Okay, continuity for bilinear maps amounts to boundedness. So again, psi of vw, this is minus v round dot round w. Okay, so psi of VW applied to H, this thing is minus VHW. And then the norm of psi of VWH, this is the norm of minus VHW, okay, which is the norm of VHW, and which is bounded by norm V times norm H times norm W for the same argument that we did above. Okay, so since this thing is valid, this map, which is linear, okay, it's bounded by, so this is true for all H, therefore norm psi of VW, okay, as a linear map is less than or equal to the norm of V times the norm of W. And well, this holds for all V and W as well. So that's why the bilinear map psi, okay, is bounded, okay, so psi is bounded, i.e. continuous, and norm psi is less than or equal to 1. Okay, so psi is continuous. Now the other thing is that phi inverse is continuous, right? So where is, yeah. So, oh, sorry, phi is continuous. So, psi is continuous and phi is continuous, and therefore this entire map is continuous. This entire map is nothing but our map d phi. D phi was the thing, which is psi of u inverse, which is psi around phi. So therefore, d phi is continuous. Okay, and maybe there's something I should make very clear here. So let me try to make it. But let's draw the conclusion now. So therefore, d phi is continuous. Okay, on isom EF. Okay, and therefore phi is of class C1 on isom EF. Now, why is the map? So I was saying the map, since phi is continuous, okay, the map phi is continuous. Now, this is something that we will be seeing in the section related to, which is what we're going to be starting with if we have enough time today, the section about the landing inside the product of non-vector spaces. It can be seen from there, it can be seen from the very definition of continuity. Okay, so if you look at phi of u plus h minus phi of u, okay, this is phi of u plus h minus phi of u, and this thing is just phi of u plus h minus phi of u, okay, comma phi of u plus h minus phi of u. And whichever norm you take on the product, let's say you take the maximum norm, okay? So the norm, okay, of phi of u plus h minus phi of u, okay, in infinity norm, the maximum norm, okay, this is gonna be the maximum, choosing the maximum, okay, between the norm of phi of u plus h minus phi of u, the first component, okay, and the same thing, right? The same thing, which is the second component, okay, which is gonna be just norm of phi of u plus h minus phi of u, okay. And since I know that phi is continuous, okay, as h goes to 0, this quantity will go to 0, and therefore phi comma phi is a continuous map, okay. So enough with this. Now let me look at the book of Cartan just to see if there are any notes here that we should be talking about. Yeah, so they talk about, so page 32, okay, page 32 in Cartan. There's this note that in the special case where the two non-vector spaces E and F are the reals, so in the special note, okay, when E is the reals and F is the reals. This is just talking about the map, okay, which is mapping X to 1 over X, right? In the case of the reals, the isom of EF, okay, is just R star. Okay, the isom of RR, it can be identified with R star, or if you want, R minus 0. Okay, and then the statement, our statement, okay, is just the following. It's just that the map x maps to 1 over x is differentiable, okay, and its derivative, so x maps to 1 over x prime, okay, at the point A is minus 1 over a squared. Okay, why is this the case? Because we are looking at minus u inverse around h around u inverse. In the reals, this is just minus h over u squared. Why? Because the u inverse and u inverse go downstairs. Okay, so let's write it more explicitly. This is minus, so u inverse is 1 over u, and h is h, and u inverse is 1 over u. So we're talking about this thing, okay, which is h minus h divided by u squared, okay, and the h here is just so for maps f, okay, from the reals to the reals, or from an open subset of the reals to the reals, their derivative, okay, is not particularly a map, okay, like in the general case, but it can be identified with a map as well, right? So if we talk about the map, let's say f of x equal to x squared, okay, we compute f prime of x to be 2x, but yeah, but on the other hand, we can also identify f prime with the map which maps h to 2x times h, okay, this linear map in h. So this h will appear whenever we are talking about the reals, okay, and will be coming from the definition of derivative, which tells you that you have df of x applied to h. when d of x here is 2x going to be applied to h, and applying d of x to h here is just multiplication. There's no, h is not an argument of the map df of x. Df of x is not a map, it's a point, okay? It's the image of x under df, okay? And applying it to h in this context just means multiplying it by h, okay? That's why we are actually saying that the derivative of this map, which maps x to 1 over x, its derivative is the map which maps x to minus 1 over x squared, okay? That's exactly what we are saying. And yeah, so this is the compatibility that we are talking about. So when you restrict, so the idea here is that when you restrict the special cases E equal R and F equal R, which are valid cases because they are part of, so R and R, of course, they are isomorphic to each other, they are the same space, and R is a Banach space, right? So I talk about Banach spaces, and the isom of them, okay, will be identified with with R star, okay? And what we proved above, or the theorem above, should also apply to this situation, and it applies just like we saw now, okay? Now let's talk a bit about functions which take values in product spaces. Okay. I believe we are in place to start with a yet another exercises solving session. I think next session will probably be about solving exercises and problems. Yes, let's talk about this thing because it's easy and because we will need to do it anyway. So now in section 5 of chapter 2, Carta, okay, in our terminology, okay, so Carta, section 2.5, okay, so we're on page, where's this page, okay, it's page 32, page 32 in Carta, okay. The title of this section, okay, is functions with values in product of, now here Carta insists to say product of Banach spaces, but we really don't need the spaces to be Banach, we just need it to be non-vector spaces. So let's say for us this is not Banach, this is product of non-vector spaces, okay? We really don't need any Banach assumptions here. There's no need for completeness, okay? At least not directly, okay? So let f definition, okay, definition of two special functions. Let f be equal to f1 cross f2 cross fk, just a Cartesian product of some non-vector spaces. Okay, so each fi being a non-vector space. Okay, and you can give f any norm, any product norm you like. Okay, so any product norm. Why am I insisting on saying a product norm? Because we really need it to be a norm depending on the individual fi's. Okay, the individual f1, f2, or fk. Right. So this map, okay, which is the projection on the coordinates. So define pi for each. So let me write. Okay, for each I from 1 to k, define the map pi, so p sub I, from f, which is the product of the fi's, or let's call it product of the fj's here, just not to confuse, okay, into fi, because I is fixed, okay, given by pi of x equal to xi. So what's this mean? Okay, x being inside f, okay, is saying that x is some x1, x2 up to xk, okay, where for all j, xj belongs to fj. Okay, so then what I'm doing is that I'm taking this x1 up to xn and I'm mapping it to its ith coordinate, okay, which is an element of fi. So that's literally projection the way we understand it. So for example, if you are inside R2, okay, this projection map, how does it look like? So let's, instead of calling them x and y, let's just call them x1 and x2. Okay, so x1 and x2. Then your map P is given by, so P1 of say P1 of AB, okay, P1 of AB is just A, and P2 of AB is just B. Okay, what it's doing is that, let's say you have a point here, okay, the point say 3 comma 2, okay, then well, P1 of 3 comma 2 is equal to 3. We are projecting on the x1 component, which is 3. P2 of 3 2 is equal to 2. We are projecting on the y component. Okay, so that's projection. It literally means projection. Okay, orthogonal projection in the case of the reals. Generally speaking, just projection on the ith coordinate. And the special map. Okay, we'll also define a special, another special map UI. Okay, so UI for each given I. Okay, it's going from fi into f, which is the product of the fj's, to each x. It's called to each xi. It's associating ui of xi equal to the element of the product which has, so ui of xi has components equal to 0 everywhere except at the ith step, or at the ith component, okay, where it is equal to xi. Okay, so it's injecting your xi, which is taken from one of the spaces which are constituting the product. It's injecting it somehow into the f. Okay, so remarks. Okay, remark. Each pi, let's say each pi is surjective. Okay, meaning an onto map. Why? Because give me anything, give me some z. Okay, I can then do pi of 0, z0, etc. They get a z, where this is the ith component. Okay, so it's surjective, and each ui is injective. Why is this the case? Because, well, if ui of some xi equals ui of some ai, okay, then what I have is that this thing 0 0 xi 0 blah 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 0 equals 0 blah blah 0 ai 0 blah blah 0. Okay, and then this thing implies that xi is equal to ai because both of them are at the ith position. Okay, so indeed ui is injective and pi is surjective. That's true for every I. Okay, now remarks. Okay, so some remarks are due. Notice that, so first thing you notice, okay, notice that if you do pi composed with ui, okay, so ui is going from, as you said, fi into the product, which is f, and the pi is going from f into, so fix an I here, fix I, fix some I between 1 and k, okay, so the ui is going from fi into f, it's injecting your element into the product, and pi is projecting, okay, it's projecting your vector into the ith component. So pi is going from f to fi, okay, and then so I can do pi around ui, right? And what happens when I do this? So let's take let xi belong to fi. Okay, then pi around ui of xi, this thing is pi of ui of xi, okay, which is pi of zeros up to the ith component, which is xi, and then the rest is 0. And we are projecting this thing. When we are projecting it, we're going to get xi. So we conclude that pi around ui of xi is equal to xi. This is true for all xi in fi. So therefore, okay, the map pi around ui is the same as the identity of fi. So you want to write like this, identity of fi, or if you want, you can just write 1, okay, where no ambiguity can arise. The second thing you should notice is when we do the opposite thing. So again, ui is going from fi into the product, and pi is going from big F into fi. I can also do ui composed with pi. Okay, but this thing is going from f into f. And what's happening with this thing? ui around pi of a certain x, okay, x is in f, x is some x1, xn, okay, ui of pi, so let's say ui around pi of x, this is ui of pi of x, this is ui of pi of x is just projecting the, so it's xi, okay, and then this is making it into a 0, 0, xi, 0, blah, 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 0. Okay, and this thing is 0 everywhere except at the ith component where it's equal to xi. And that's why if I do u1 around p1 of x, I'm going to get x1 and zeros. If I do u2 around p2 of x, I'm going to get 0, x2, zeros, and so on till I reach k. So I have uk around pk of x. This thing is 0, 0 till I reach the xk. If I add these up, okay, what do I get? So the sum, so therefore the sum, okay, of ui around pi I equal 1 up to k of x, this thing is the addition of these. Okay, this and this and this and whatever is in between. It's going to produce literally x1, so let me change the color. It's going to produce literally x1, x2 up to xk, exactly this thing, which is x again. So therefore, what I conclude is that the sum I equal 1 to k, ui around pi of x, this thing is equal to x. Therefore, the mapping ui around pi summation I equal 1 to k is exactly the identity of f. Okay, so identity of f. Or if you want, just write 1. Okay, so recap of this remark. Okay, recap. The first thing is that pi around ui is the identity of fi, and the sum, say, of uj around pj, j equal 1 up to k, this thing is the identity of f. Okay, and these two things will help us prove the following proposition. Okay, the proposition just says something that you know sort of from previous courses. So proposition, okay, take a map f, so let e f1 up to fk be normed vector spaces. Okay, let f be the product of the fi's, so f1 cross f2 up to fk. Okay, and let f from an open subset u inside e into big F. Okay, and let u, so let a belong to u. Okay, then f is differentiable at a if and only if, okay, each component, okay, so quote unquote, because I need to define this, each component of f is differentiable at the point a itself, okay, at a, which is the same as saying, so I'll define what means for each component of f. Okay, so these two are equivalent. That's what I want to prove. Okay, what's a component? A component of f. Well, since f is going from e into f, which is the product of the fi's, for each I can look at the projection, so pi around f. What's this representing? Suppose you have just a function that you know as usual, gamma, let's say gamma of t, okay, equal to gamma 1 of t, gamma 2 of t, gamma 3 of t. Okay, suppose the gamma is some position of a vector, okay, and you're doing vector calculus. So gamma is a function going from the reals, some subset of the reals into R3, let's say. Okay, the first projection of gamma, so P1 round gamma, okay, of t is just gamma 1 of t. So literally P1 round gamma is just gamma 1 as we know it. And we know that gamma, okay, is differentiable if and only if gamma 1, gamma 2, gamma 3 are all differentiable. That's what we are talking about here, sort of, okay. So pi around f, I call it fi, okay, And these fi's, I call them the components of f. Okay, so what we are saying here is that f is differentiable at a if and only if for all I fi is differentiable at a. Okay, and to prove this thing, it's really not difficult. Okay, so you just need to realize what's the expression of f in terms of its component, and then it becomes a piece of cake. So proof, first direction, suppose f is differentiable at a, right? Yeah, so because fi is just f, so just pi around f, okay, f is differentiable at a, so you just need to prove that pi, so required to prove that pi is differentiable at f of a. Okay, in fact pi is differentiable everywhere. Why? Pi is a linear map, linear and continuous. Why? Well, pi is going from f into fi. Look at the norm of pi. Okay, so let alpha belong to f. Okay, then pi of alpha in norm inside fi. Well, this thing is just the norm of, what's pi of alpha? Just project on the ith component, alpha I in fi. And this thing is less than equal to the norm of alpha in infinity. Just take the infinity norm of the product. Okay, because the infinity norm picks out the maximum. Okay, and the maximum between the components is certainly bigger than one of the components. Okay, bigger than any of the components. So therefore, pi has norm less than or equal to 1 as a linear map. Okay, and to show that it's linear is really very easy. Okay, pi is just projecting. If you are adding two stuff, projecting this addition, then you get the addition of the projections. Okay, and therefore pi is differentiable, so therefore fi is differentiable for all I. That's the first direction. Okay, second direction is that again, you are assuming that fi is differentiable for all I. Okay, now we employ the thing that we were talking about in the remark. Okay, since the f is, so fi is equal to pi around f. Okay, they want a way to write f in terms of the fi's. So what I'm gonna do, okay, is gonna be employing the fact that so look at ui around, or let's say uj around pj. Okay, this being equal to the sum of this thing being equal to the identity. Okay, this implies that the sum from j equal 1 to n of uj around pj of f itself, okay, f of x is equal to f of x. Okay, and then we're really saying, okay, f is equal to the sum of uj around pj around f, okay, from j equal 1 to n. But I know that this part here, pj around f, is just fj by definition of fj. So therefore, f is equal to the sum of uj around fj. Okay, and for the same reasons as above, okay, uj is a linear map, linear and continuous. So therefore, it's differentiable. So therefore, f is the sum of differentiable functions. Because if uj is differentiable and fj is differentiable by assumption, then f, so therefore f is differentiable at a. Okay, so f is differentiable at the point if and only if its component functions are differentiable at the same point. Now a remark. Okay, so a remark. If f is as above, so if f is as above, okay, then df at a point a, okay, this is just the sum, okay, of uj composed with dfj at a. Okay, if you want, you can write it, so sum from j equal 1 to k. If you want to write it as this, so f prime of a is equal to the sum of uj composed with fj prime at a, okay, from j equal 1 to k. Why is this the case? Well, I know that f is the sum of uj round fj, okay, j equal 1 to k. So then df of a, this is d of the summation uj round fj, j equal 1 to k at a, I know that the derivative is linear, so this is the same as the sum j equal 1 to k of the derivative of uj round fj at the point A. By the chain rule, this is the sum of duj at fj of A dfj at A, composition of course. Okay, but uj is a linear map, linear continuous map, so its derivative is equal to itself. So this is just the sum from j equal 1 to k of uj composed with dfj at A, which is what we wanted to prove. Okay, so that's it for today. Okay, next time we're gonna be continuing with the notes. Okay, and then hopefully soon enough we'll be able to start with or go back to solving exercises and problems. Okay, when we have enough things to do, enough material at our hand. Okay, so thank you for watching, and I'll see you next time.